Hi, in this video, I'm going to continue on the topic chemical reactions and energy. And this time we will move on to the chapter called Hess's Law. Now, in the previous videos, we've been talking about a calorimetric experiment, and we know that by performing calorimetric experiments, we can find out the heat change of a reaction and therefore find out the enthalpy change of a reaction. However, in some situation, these calorimetric experiments doesn't work. For example, if you look at this, now in this reaction, carbon reacts with oxygen to form carbon monoxide. If I ask you how can we find out the enthalpy change of this particular reaction, you may suggest, sir, we can actually burn the graphite. As we burn the graphite, the heat released will be used to heat up a beaker of water, and by finding out the heat absorbed by the beaker of water, we are able to find out the heat released by the reaction, and at the end, find out the enthalpy change. Sounds fair enough. However, if you think about it a little bit in detail, you realize that when we burn carbon, it is most likely to form carbon dioxide instead of carbon monoxide. Well, even though it forms carbon monoxide, the carbon monoxide would be the minor product. So it looks like we can't simply perform a calorimetric experiment by simply burning the graphite, right? So how can we actually find out the enthalpy change of this particular reaction? Or this one, if you think about it closely, this is actually the enthalpy change of formation of carbon monoxide. So it seems like it doesn't work. So now you realize that calorimetric experiment is something what we call a direct method to find out the enthalpy change, because we are finding out the heat change of that particular reaction directly. But in this case, a direct method doesn't work. So that's why we need to think about something perhaps indirect. So in the later on discussion, we are trying to go for an indirect method to find out the enthalpy change of a reaction. Now, this indirect method is based on the Hess's law. So let's have a look at Hess's law and see what does it talking about. Now let's look at the definition, which is quite important. It would be best if you memorize it. It says that the Hess's law states that the overall enthalpy change of a reaction is the same regardless of the path it takes. What does it mean by that? Usually, I will use an analogy. Okay, so think about it. Suppose you want to travel from Chunwan to, let's say, Central, right? So you want to take it by MTR. And how can you arrive to Central? Now, there are a couple of ways, and one of the easiest way, the most direct way, is to take MTR from Chunwan all the way to Central Station. You don't have to change the lane, you don't have to walk around, you just have to take it from Chunwan to Central, that's it. So this is like route number 1. What about route number 2? You can actually take from Chunwan Station to Lai King Station, and then you switch to Dongchong Line, and then you travel to the Hong Kong Station, alight from there, walk a little bit to the Central Station. Again, you can actually reach the Central Station. If I ask you, which route costs more? You realize that actually no matter how you travel, they cost the same amount of money, right? So you will be spending the same amount of money regardless of the route it takes, as long as it is from Chunwan to Central, it costs the same money, okay? So this is exactly what Hess's law is talking about. If you look at this diagram, if you want to react the reactant R to product P, you can obviously go for a one-step direct way, okay, and this will be the delta H. But you can actually change R into, let's say, A, B, C, and lastly, C is reacted to form P, right? So even though you take a one-step route or a four-step route, we say that the energy involved would be the same. So that's why we will say the delta H here is equal to delta HR plus delta HA, delta HB, and delta HC. And this is exactly what we've been talking about here. So this route is the same as this route. Okay, so that's the idea. That's the idea. So just now, in this situation, if we cannot find out the delta H directly, perhaps we will have to think, oh, is it possible to have like an alternative path, perhaps with more than just one step? And if we are able to improvise, devise a path where at the end of the day it reaches to the carbon monoxide, then perhaps we are able to find out the standard enthalpy change of formation of carbon monoxide in an indirect way. So this is exactly how the Hess's law works. All right. Now let's have a look at an example down here. So it says that nitrogen dioxide can be formed from nitrogen and oxygen by either a one-step path or a two-step path. So the one-step path would be a very straightforward reaction. N2 reacts with O2 to form NO2. Right? Now the two-step path is that the N2 first reacts with O2 to form nitrogen monoxide, and the nitrogen monoxide undergoes a further oxidation to form nitrogen dioxide. Right? Now you realize that if you try to combine these two equations together, if you try to combine them together, you realize that the carbon monoxide can be cancelled out, right? Because if you add them together, like these four items will be the reactant, these two items will be the product, then you will have nitrogen monoxide on both sides, then you can cancel it out. So you have these two cancel out, and you also notice half O2 plus half O2 equals to 1 O2. Then it would be the same as the first reaction here, right? So that's why when these two added together, it equals to the first reaction. So that's why we will say that no matter you take a one-step path or the two-step path, actually the enthalpy change involved would be the same. 33 plus 35 equals to 68, okay? So if you can't find this value, if you can't find this enthalpy change directly, but you are somehow able to find out the enthalpy change of these two, then you can simply using these two enthalpy terms to indirectly calculate the enthalpy change of this reaction. All right? So if you go down here, you see how this one, the delta H naught equals to delta H naught 1 plus delta H naught 2. Okay, so that's the idea. Okay, that's the idea. So, in other words, we are trying to manipulate equations in order to achieve the equation that we want. Okay, now let's look at the right-hand side. Let's look at how we practically deal with some of these questions. How do we practically combining equations or manipulating the equation so that we can get what we want indirectly? Okay. Now here, this part is called the enthalpy change cycle, because just now we see that here there is a cycle, right? We are trying to construct a cycle. So here we try to consider the energy change cycle. Okay. Now, if you look at these given equations, okay, actually this is corresponding to our first question here. Okay, now carbon reacts with oxygen to form carbon dioxide, carbon reacts with oxygen to form carbon monoxide, carbon dioxide reacts with oxygen to form carbon dioxide. And you realize that here, this is the first equation, and the delta H, we put it on the top here. This is negative 394 kilojoule per mole. Okay, and now from here, you realize that actually carbon can undergo oxidation as well to form carbon monoxide following the second equation. So this carbon can actually react with half mole of oxygen to form carbon monoxide. So after carbon reacts with half mole of oxygen, it forms carbon monoxide, right? And this one would be negative 111 kilojoule per mole. Okay. Now, since this reaction only consumes half mole of oxygen, it should have half mole of oxygen remain unchanged. Okay. After reaching this stage, you realize that carbon monoxide can actually react with half mole of oxygen gas to form carbon dioxide, according to the third equation, right? So these two react to form this. Now, But you realize that according to this equation, it is 2 carbon monoxide reacts with 1 oxygen to form 2 moles of carbon dioxide. But here we only got 1 carbon monoxide. So if you look at the enthalpy terms, yes, we are using the delta H naught 3 here, but we have to divide it by 2 because we are forming 1 mole of carbon dioxide instead of 2. Okay? So after doing this, you realize that, hey, we have constructed a cycle. Now, when we talk about cycle, it does not necessarily means that it is all in clockwise direction or they are all in anti-clockwise direction. It doesn't have to be like this. Well, if you really want to be like this, it is still okay, but we will talk about it later. Now, when we look at the energy cycle like this, what we're trying to do is we're trying to think about a starting point and a destination. Because remember, one of the characteristics of a cycle is that every point could be a starting point, every point could be an end point, right? This is what we call a cycle. So here, let's just say I will take this one as the starting point, and I'll take this one as my destination. Then, if you want to go from here to here, you can either go for the red path, straightforward, or you can go for a 2-path reaction pathway. First becomes this and then becomes this. So we will say delta H naught 1, the red one, equals to delta H naught 2 plus the delta H naught 3 divided by 2. Okay, so this path equals to this path. All right. So this is how we can make use of the thermochemical equations to establish an enthalpy change cycle, which tell us how we can make use of different equations to find out a certain enthalpy change. Now here, you see we have all the enthalpy terms, right? If we go back to here, just now we try to find out the enthalpy change of this particular reaction, which is this one, right? Carbon reacts with oxygen to form carbon monoxide. So assume that we don't have this enthalpy terms and we are asked to find that out. Then we can actually make use of the red one and the purple one. We are able to deduce this one, right? Simply using this equation, we don't have delta H naught 2, but we have these 2 terms. And perhaps these 2 terms can be found out directly by calorimetric experiment. If we are able to find out these 2 terms by the calorimetric experiment, then we are able to calculate the delta H naught 2 by Hess's law, by an indirect method. So that's the idea. And in reality, it is much more easier to carry out calorimetric experiments of the standard enthalpy change of formation of carbon dioxide as well as the standard enthalpy change of combustion of carbon monoxide. Right? These 2 we can carry out calorimetric experiment easier. Okay? But this one is quite difficult. We did talk about that at the beginning, right? So that's the idea. So these are the notes that I have already mentioned. So I did talk about it at the very beginning in this series of videos. Whenever we are writing the chemicals or the equation, you must include the physical state. This is the same as the energy cycle. Okay, you must have here you must have the physical state. You must have the stoichiometry. You must have the unit. The unit is mentioning the kilojoule per mole here. You must include all of these when we are constructing the cycle. Okay. Now here, this is just to again discuss why it is important using just now the standard enthalpy change of formation of carbon monoxide, which can only be derived by an indirect method. So you can read it yourself. Now let's have a look at a practice question to see if you are able to interpret this enthalpy change cycle. So you know the drill, pause the video and attempt the question yourself, and then we see how it works. Okay, so let's have a look. So the main reaction is A plus B forming C, and you know it has another, and it forms a cycle, all right? Now here, A, state Hess's law. So Hess's law, it states that the enthalpy change of a reaction is the same regardless of the reaction path it takes. Okay? You can refer to my notes easily. Now B, determine the standard enthalpy change of the following reaction. So here, C becomes A plus B. Now from this cycle, you see that A plus B equals to C. Now they are asking, what about C becomes A and B? So just go back. Now when it goes back, you can simply reverse the enthalpy terms. Okay, so this one is simply positive 100 kilojoule per mole. Okay, when you flip the direction of the arrow, you also flip the sign of the enthalpy terms, but the value should be the same. Now here, BII, so 4D becomes 2E and 2F. So it has to do with this equation, right? So this time we don't have to flip it, but this time we have to multiply the stoichiometry, because here is 2D become E and F. So here basically we have 300 minus multiplied by 2 equals to 600 kilojoule per mole. Okay? And what about 3 here? A reacts with B to form E and F. So A and B is over here. E and F is over here. So actually, you can make use of this route or this route. But here we don't have delta H naught 4, right? So perhaps we can look at this route. So A plus B can first react with D with the enthalpy terms here, enthalpy change here, and then the 2D here reacts to form this one. So this path consisting of these two processes, we just have to add the enthalpy terms together. So we can put down delta H naught 2 plus delta H naught 3 equals to 200 plus 300, which is equal to positive 100 kilojoule per mole. Okay? Then part C, determine delta H naught 4. Okay? So determine delta H naught 4. If you want to find this one, you can make use of the Hess's law. So A reacts with B can form E and F. And it can be done so by following this path or following this path. Okay, it doesn't matter. So if it follows this path, okay, if it follows this path, this is exactly what we have determined, which is positive 100, right? So positive 100, this is the yellow path, okay? And this yellow path will be equal to perhaps the blue path, which is here. Right? Yellow path equals to the blue path. So the blue path is involving delta H naught 1 and delta H naught 4. So this one you can put down, okay, delta H naught 1 and delta H naught 4. Okay? Here. So delta H naught 1 is negative 100. Delta H naught 4 is what we are looking for. So negative 100 plus something equals to positive 100. So delta H naught 4 must be equal to positive 200 kilojoule per mole. Okay? So this is how we can make use of the Hess's law as well as enthalpy change cycle. Okay? Now, D here. Suppose all chemical species in the cycle are in their standard states and both A and B are the elements with a thermochemical equation including the enthalpy change for the formation of D. Okay, what a mouthful. Forming D, okay? So first of all, forming D here. To form D, that means it must be formed from its constituent element. And it is formed from A and B, and just now it said that A and B are the elements. So to form D, it must coming from A and B. Alright? But you also realize that A reacts with B to form 2D. right? But now, according to the definition, if we want to form D, D must be set as 1 mole. Okay, so D must be 1 mole. So therefore, here it must be half. Okay, and then because this is half mole of A reacts with half mole of B to form 1 mole of D, so the enthalpy terms must be halved as well. So the delta H naught F D here must be equal to -100. Okay.